All right, today we're tackling one of the all-time greats in computer science, Dijkstra's algorithm. You know, the one that's basically the master of finding the shortest, fastest, or cheapest way to get somewhere.
So let's start with a question you've probably asked yourself a million times. I mean, whether you're mapping out a cross-country road trip or just trying to get to a coffee shop across town, you're trying to solve this exact computational problem. And this is precisely what Dijkstra's algorithm was born to do.
So let's just put a name to it. We're talking about the fastest path problem. It's a fundamental challenge that pops up absolutely everywhere.
Okay, that definition sounds a little dense, right? But let's just break it down real quick. Single source just means we're starting from one spot. A weighted graph is basically just our map, where every road has a weight, like the distance or the time it takes to travel. And the really crucial part, we're going to come back to this, is non-negative weights. All that means is that no road can magically give you time back. So, put it all together, and Dijkstra's finds the quickest way from your starting point to everywhere else.
And this idea, this brilliant idea, has been with us for a while. It came about back in 1956 from the mind of Dutch computer scientist Edgar Dijkstra. And he wasn't trying to solve some abstract math problem. He was literally just trying to figure out the shortest way to travel between cities in the Netherlands. From that very practical need, he built an algorithm that is now the absolute bedrock of GPS, internet routing, you name it. Its simple elegance is just timeless.
So how in the world does it actually work? Well, let's forget about code, forget about the heavy math for a second. The best way I've found to really get it is with a little analogy I like to call the sticky note method.
I want you to picture a big map of cities and roads spread out on a table in front of you. You're standing at your starting city, and your mission, should you choose to accept it, is to figure out the absolute fastest way to get from where you are to every other city on that map.
Here's what you do. First, you take a sticky note, write a 0 on it, and slap it on your starting city. I mean, it takes 0 time to be where you already are, right? Then you put sticky notes on every single other city that say infinity, because right now, you have no idea how to get there. Now the fun starts. You look at all the cities you haven't visited yet and pick the one with the smallest number on its sticky note. Right now, that's your starting city with a 0. You finalize it. Now from there, you look at its direct neighbors. If it takes, say, 10 minutes to get to city B, you go over to B's sticky note, cross out infinity, and write 10. You do that for all its neighbors. And then you just repeat. Find the next unvisited city with the lowest number, finalize it, and update its neighbors. You just keep doing that over and over.
You know, this whole process of just always picking the closest city you know about, there's a formal name for that. It's a greedy approach. This quote here nails it. You're just greedily choosing the best-looking option you have at every single step.
But here's the million-dollar question. Why does this greedy thing even work? It feels a little too simple, doesn't it? Like, how do we know for sure that once we pick that city that's 10 minutes away, there isn't some super weird roundabout path that could have gotten there in 9? Well, the secret sauce is that non-negative rule we talked about. Since no road can take away time, any other path to get to that city has to go through other cities first, and each of those steps will only add more time. So that first path we find to the closest city, it's guaranteed to be the shortest. That's the real magic here. A simple, local choice at each step gives you the perfect global answer. It's just beautiful logic.
Okay, the sticky note method is great for building intuition, but now let's get into the nitty-gritty. Let's talk about how this actually translates into code, performance, and a few very important rules of the road.
And this right here is the biggest one, the golden rule. If you remember one thing, make it this. Dijkstra only works if all the weights are 0 or more. The second you have a path with a negative value, think of it like a magic portal that gives you time back, the whole greedy logic just completely falls apart. That guarantee we had is broken.
So what do you do if you do have negative weights? Well, you reach for a different tool in your toolbox. You use an algorithm like Bellman-Ford. Sure, it's a bit slower, but it's built to handle those weird cases. It's all about knowing your algorithm's limits.
Now, how fast is this thing in the real world? Well, it kind of depends on how your map is set up. If you have a dense graph where pretty much every city is connected to every other city, a simple approach is fine. But most real-world maps, like road networks or the internet, are sparse, meaning cities only connect to a few neighbors. For those, we use a really clever data structure called a binary heap. Just think of it as a super efficient way to always know which sticky note has the lowest number, without having to scan through all of them every single time.
And that clever trick is what gives us this performance you'll see everywhere, O of E log V. Now don't let the letters scare you. All V is the number of cities, and E is the number of roads. And that efficiency is what makes this algorithm so incredibly powerful, even on massive networks with millions and millions of roads.
All right, enough theory. Let's bring this back home and talk about where this algorithm is running right now, all around you, probably without you even noticing.
I mean, every single time you pull out your phone and ask for directions, some version of Dijkstra's is firing up, calculating the best route based on traffic. When you're watching this, routers on the internet are using this same logic to find the most efficient path to send all those little data packets to you. Seriously, it's everywhere, from calculating network lag to optimizing massive supply chains. And hey, if you're ever prepping for a tech interview, listen up. Here are the takeaways that'll make you look like a real pro. First, always state the non-negative weight assumption right up front. It's the key. Second, talk about the performance trade-offs, and definitely mention that a binary heap is the way to go for sparse graphs. For bonus points, explain that if you only care about getting to one specific city, you can just stop the algorithm as soon as you find it. And finally, show you know the landscape by mentioning when you'd use something else, like Bellman Ford if you've got negative weights.
So Dijkstra's algorithm is an absolute champion at finding the best path when every step you take has some kind of cost. But that leaves us with a really fascinating question to think about. What happens to the whole idea of a shortest path when some roads don't just cost you nothing, but could actually give you time back? Well, that's the strange and wonderful world of negative weights, and trust me, that's a whole other adventure.